join. Our first speaker should be Kevin. I don't know, Ari, do you know if Kevin is joining? Here we go. Hi, Kevin. Great. Okay. Well, maybe. Hi, Kevin. So great. Welcome, everyone, to this session on tools and configurations. We have some papers in this session from the technical track and some from the software engineering in practice track. So I think we've got a very nice, interesting set of papers to look at and presentations. My name is Robert Chatley from Imperial College in London, and I'll be just facilitating this. I think as other sessions you've seen, we'll have the 6 presentations, first of all, 5 minutes each, and that should give us plenty of time to discuss afterwards. Hopefully there'll be plenty of discussion and questions. And we'll go through the presentations in the order that they are in the full program. So I think Midspace might show a different order, but that will mean that we'll start off with Kevin, then we'll have Anastasia, then Yintong, George, Clemens, and Edward to finish, if that's okay. So with that, I think if Kevin, you're able to start, I'm happy to hand over to you.
Yes, thank you. Just checking if everyone can hear me all right.
Okay.
Okay. There we are. One second.
No problems.
Is this working for you?
Yeah, that looks good.
Okay, thanks for the heads up. Hi everyone, welcome. My name is Kevin Anderson, presenting from holiday in Scotland, where the weather is true Scottish, so it's cloudy, rainy, and some sunshine, so I hope I'm in the right spot. I'll take 5 minutes of your time to present our work around challenges in applying continuous experimentation, and this is really a perspective from practitioners. Now, the research team is a joint collaboration from people from Technical University of Delft. So Arie van Deursen, also in the call, professor in software engineering. Charles Chung, he did an internship at ING. Jan-Willem Mannen, my former manager at ING, and Denise Visser, product manager experimentation from Bol.com. And myself, well, previously at ING, where I did this work, but now a product manager experimentation at Vista, and also pursuing a part-time PhD together with Arie van Deursen at Delft around this fascinating topic. Now, what is this all about? Maybe a quick introduction. I think this is a concept that everyone knows, but A/B testing or experimentation is just being adopted on a massive scale across many companies. There is a big shift between companies who invest a lot in central teams and also enable it on a large scale. And I would say the rest of the company. So many online businesses do A/B testing. In a nutshell, that is creating different experiences where we randomly assign people to those different experiences to see what is actually the impact on an important KPI or a set of KPIs that business finds important. So in this case, it could be a visual change, but it could also be an algorithm. It could be any change that has or could have a potential impact on customers. Now, the term continuous experimentation means that this is not on an ad hoc basis, but in the end, each and every experiment or each and every feature change will be run out as an experiment. And that is not the case for the majority of companies. So let's look at what we already know. I think one of the biggest examples of one of those companies that does it on a large scale is Booking.com. Also writing quite some papers on this topic, how to democratize online controlled experiments. Booking.com has been doing this for 15, maybe 20 years. So they have a lot of knowledge, a lot of investment in infrastructure, but also processes, people. So this is a central component in their way of working. But this is Booking.com. Some people from that company, together with people from Microsoft and Outreach, wrote a paper on how to get this flywheel of adopting of experimentation up and running. And they present here the flywheel around A/B testing, where the first big push is often the hardest. Getting interest around experimentation, getting interesting results out in the organization is oftentimes the hardest thing. If that is happening, then there will be more interest, there will be more investment, more people can run experiments, and more results will probably happen. So they present here this flywheel model, and I think that is a good model that many people in other organizations can use to adopt experimentation as well. Now, the problem here a bit is that this is being written down from companies who already get this experimentation philosophy and have successfully implemented. Now, there are other companies, and I think I'll need to switch to the research method that we want to do here, because we wanted to look at 4 research questions here. Now, the first one is, how do practitioners actually define and apply experimentation? What do they think is the perceived value of that? What do they see as the blockers in doing more experiments? And then, of course, how can we advise organizations to solve these blockers? And this is, I think, in context of the flywheel model, it's not like one big bang that you implement something, but it's really like chipping down and removing blockers that are already there to help more people in a organization to run experiments. Now, the context that we did this in, you probably guessed it from the introduction, 2 companies are highly involved here, ING and Bol.com. Both have a strong base here in the Netherlands. Strong presence, market leaders in their domain, well-known brands, and also have invested in an in-house experimentation tool. So I think they're a little bit ahead of many other companies here. The difference is that there are 2 completely different companies, right? One, Bol.com, is a completely e-commerce platform operating mostly in the Netherlands, but also in Belgium. And ING is a financial services company, market leader in the Netherlands and in some other countries, but has offices.
5 minutes. We've got to 5 minutes now. So if you could just summarize the findings.
Oh, sorry. Okay, thank you. So we did the interviews and a survey. I'll skip this part. I think this is the meat of the paper. So the most important blockers that people experience is that leadership does not give it priority. There are a lot of dependencies. Few people have experience in doing it. That really hinders how to solve this. There's no or hard to use tooling in place. So although there is a platform, some people cannot access it yet. And many people have issues with setting up metrics and really defining a proper experiment. So we've come up with a list of improvements, and I think the 4 takeaways from you are: one is that it's really important to create a common language around experimentation. So leaders really should lead the transition to become an experiment-driven company. It starts at the top. Companies need to invest in dedicated teams or even a center of excellence. And some blockers even go beyond the scope of experimentation. So yeah, there's all probably the most important ones to solve first. Sorry for going over time, but thank you for your time.
That's okay, Kevin. And I'm sure people will come back and we'll find out more during the discussion later as well. So I'm sure there's much more time. So just to move on then to the second presentation, I think the second one is Anastasia.
Yeah. Hello.
Anastasia.
Second. Do you see my screen?
Yes.
Do you see me? Okay. Okay, let's start. And hello, everyone. My name is Anastasia, and I'm a researcher at JetBrains Research. And I would like to present our work, Reflect, a library for compile time reflection in Kotlin. First, let's define what reflection is in general. Reflection can be defined as the ability of a program to manipulate its data, something representing the state of the program during its own execution. A simple reflection example is type identification that is common for model languages, for example, instance of and is operators in Java and Kotlin respectively. In our work, we consider one of the reflection tasks. It is collecting all the classes, object expression, and functions that satisfy some search conditions. But I should note that we limit this task only to cases where all entities can be found during the compilation of the project. This reflection task can be solved by several approaches, and they can be divided into 2 groups according to the execution time: runtime and compile time. Runtime approaches usually scan all classes from the class path and use Java reflection API under the hood. The most popular approaches are reflection and class graph, but the main drawback is performance degradation caused by the class path scan. Compile time approaches usually index classes from class path during the project compilation, and next use this information at runtime to avoid scanning class path again. However, to detect classes that should be scanned, developers should mark classes or functions by special annotations manually and increase code complexity. Although this approach doesn't solve a more general task. For example, if we would like to find functions with by custom condition. All the described approaches have their pros and cons, and in this work we propose a new approach leveraging the Kotlin compilation process. It is Reflect. Reflect is a reflection library that provides means to search for classes, objects, and functions in Kotlin source code at compile time. Reflect consists of 3 main parts. It's 2DSL with core and extended functionality and a Gradle plugin to make it possible to use Reflect in another project, and the Kotlin compile plugin that implements compile time resolution of reflection queries. All the Reflect is open source and available on GitHub. The core DSL resolves 2 types of query, and the first one is finding classes and object expression with specific annotations and supertypes, and the second one is finding functions with specific annotations and signatures. An example of the query is shown on the slide. This query allows to search for all public classes with supertypes A and with annotation C, and all classes with final list will be cast to the class B. The extended DSL works resolve 2 types of queries, but are more general. The first one is for finding classes and object expression by custom condition with specific supertype. The second one is finding function by custom condition with a specific signature. The condition here allows operation with all entities properties. For example, filter entities by their name, or check if a class is open, or check if companion is object companion. An example of this query is also shown on the slide, and this query allows searching for all public top-level functions with name foo, without arguments, and with return type unit. The main part of the Reflect project is the compile plugin, but I will not describe it in detail since we're limited in time, but you can ask me after the presentation. The main idea is to replace each Reflect query with a list or set of entities that satisfies this Reflect query. For example, if we have this Reflect query and we have only one class C that satisfies this query, we replace the whole query with a list with class C, and then at runtime we will not search entities since we already have the list with them. We implemented this approach and evaluated it on the Kotlin project. Kotlin is a framework created with JetBrains to facilitate the development of serverless application in Kotlin. In Kotlin, the application startup time directly affects the overall amount of the required resources. We used Kotlin as a library with two projects, a Kotlin documentation website and a web service to shorten the web URLs. In total, we replaced 2 types of queries. In the final, the compilation time significantly increased by about 1% for both application as well as for the compilation of Kotlin itself. But the most interesting part is the difference in application start time. The overall time of the application start decreased about 14 and 70% for both projects. Moreover, the execution time of the reflection library directly correlates with the number of classes it scans. It means the larger the application is, the more improvement we can get when migrating from standard time reflection libraries, for example, reflection or class graph, to the proposed compile time reflect approaches. That's all. Thank you for your attention. If you have any question, please ask me.
Thank you very much, Anastasia. And I'm sure there'll be some questions. People can note questions in the chat, and we'll come to them later. But also, we'll have time for that decision as well.
Okay, thank you.
And so the third presentation, I think, is going to be on Arklin, and it is Yintong. Do we have Yintong? Yes. Are you ready to present, Yintong?
So, can anyone see my screen?
Yep, we can
and
see it
hear my
fine.
voice. Well, thank you very much. And hello everyone, this is Yintong Huo, a PhD student from the Chinese University of Hong Kong. Here, I would like to show our work Arklin, an automated API mention resolution technique for unformatted text. Considering mining knowledge in the online forum, the first and fundamental thing is to recognize and identify API mentions from the unstructured language. Because users in the open forum contain various technical background and writing styles, it is not easy to do so. Here comes 2 questions: how to recognize an API mentions and how to resolve the API mentions. Implementing straightforward rules such as regular expression is not flexible enough to solve the task. Investigating into the online discussion, we identified 3 challenges in the task. First is the common word ambiguity, which refers to the ambiguity between common words and API mentions. The second challenge is the morphological ambiguity, which is caused by developers rarely write a full API name in the discussion. And the third challenge is the reference ambiguity, which happens if the API list contains multiple third-party libraries. To tackle with the 3 challenges above, we propose our framework Arklin with 2 components: an API recognizer to find API mentions in the free text, and a contextual API linker which links API mentions to the exact API that it refers to. In this recognizer, we devised the self-labeling approach, which allows Arklin to escape from label-extensive annotation. This self-labeling approach works as follows. We first automatically identify possible API mentions by set of rules deriving from our observation. Then, we augment the data by replacing the potential APIs. This step allows Arklin to discriminate the context of common words and API mentions of our first challenge. In order to determine whether a token is an API mention or not, we introduce architecture. It is constructed with a conditional random field on top of a bidirectional LSTM network. We derive two-level granularity feature into our encoder to capture such semantics, the character level feature and word level feature. To resolve the disambiguation, we developed our basic idea from 3 steps. First, we narrow down the matching scope by selecting some candidates, then we filter irrelevant ones, and finally, we rank the candidates by their similarity to the API mentioned. Based on the observation that humans rarely misspell the APIs at the beginning of the word, we filter the candidates by such heuristic rules to reduce the time complexity for future comparison. Next, we filter the irrelevant APIs to resolve the reference ambiguity by training a library predictor based on the large machine language models, and in this step, only the candidates in the predictor library will be reserved. Eventually, we rank the candidates based on their lexical similarity and entity. For the lexical similarity, even though humans make some typos in spelling APIs, its lexical meaning still stay close. Here, the lexical meaning profiles the word representation learned from corpus with semantics. While the lexical similarity targets as spelling errors, we use entity similarity to address the problem that users may write the abbreviations of an API instead of the full qualified name. In this case, they write the most informative part, so the entity similarity should pose into consideration. Finally, the overall similarity is the integration of lexical similarity and entity similarity. In the experiments, we choose libraries and Stack Overflow to study with. We evaluate the overall effectiveness of Arclin. The result shows that it outperforms all baselines by a wide margin, even though Arclin is free from any labor-extensive annotations. To summarize our paper, we first display 3 challenges in API mention resolution: the common word ambiguity, the morphological ambiguity, and the reference ambiguity. Then we propose our approach, Arclin, including an API recognizer and an API linker to resolve the 3 challenges above. Eventually, with the experimental results, demonstrate the effectiveness of Arclin. And artifacts and code and dataset are released for future research purpose. And this is all about our presentation. Thanks for listening. Any questions and discussions are welcome.
Thank you very much, Yintong. Very interesting. If people have questions about this they want to note, please just drop those into the chat and we can come to those after the talks, or we will have time as well. So moving on to our 4th presentation. Next we have George on the benefits
Can you hear me?
parental builds. Yes, we can hear you okay.
Okay, I can go ahead.
Yes, please.
Okay, so good morning or hi everyone. Today I'm going to present our paper on the benefits and limits of incremental build of software configurations and exploratory study. This is a joint work with my colleague Jevahire and my PhD advisors Jamel and Mathieu, published at Technical Track of ICSE 2022. So in this paper, we are considering highly configurable systems that are configurable through the compile time options. And here we have 3 configurations with their compile time option. And to test or to ensure that these configurations build for a highly configurable system, here the configurable system is the Xterm terminal emulator. To test if it passes some tests or it builds and so on. And if you want to use the binary afterward, you have to build them, and the common practice is to clean build them, just building them from scratch or doing make clean between each compilation. But what we want to propose for software configuration is to incremental build them. So we build the configurations one after another without cleaning and letting the build system reusing the previous artifact of the previous builds. And here in this example, for instance, we can gain 2 seconds by doing so. And we wanted to explore this idea even more. So we designed an experimental approach. So for 3 configurations, C1 to C3, for instance, we we do an incremental build of every possible pair of our configuration sets, and then we check for the feasibility of incremental build by checking the build failures, if it fails or not for incremental build. We check the efficiency of incremental build by comparing the build time of the incremental build of a configuration and its clean build. We check for correctness of the incremental build product by comparing the binary size and symbols of the binary produced by an incremental build and its equivalent in clean build. And finally, we check for an optimal ordering, which is the combination of clean builds and incremental builds, and which is the chain of incremental build that is the fastest on the overall build time. And here, for instance, we could build 3 configurations incrementally in 27 minutes instead of doing 3 clean builds in 45 minutes. So we applied our experimental setup on 5 configurable systems, C-based and with the make build system. We generated 2 batches of 20 random configurations generated with feature IDE. And in our results, the lessons learned are that incremental build of configurations is feasible on highly configurable system at 78% for some cases and up to 100% for other batches of some configuration of some software. The incremental build of a given configuration can be faster than its clean build, but depends on the artifact built previously. And the produced binary of an incremental build, the produced binaries are likely to be correct at 57% of the cases, but it's not always the case. And finally, it is possible to find the optimal ordering of such that the overall incremental build time outperforms the workflow of only clean building it. And for this one, if the incremental build is not correct but fast, we take its clean build, and for the other cases, we incremental build them. So in conclusion, to sum up our contributions, we present a novel problem of incremental build of configurations, which is bringing incremental builds for software configurations. We designed an exploratory study to investigate the benefits and limits of incremental build, and we offer a quantitative and qualitative analysis of empirical results. In the paper, we draw a discussion, and we have 3 points. The first one is to encourage the developers to experiment incremental build not on the little modification during the development time, but rather on the incremental build of software configurations and finding optimal ordering to to build faster the configurations and ensure that a subset of the configuration space compiles at least. For build system designer to make a more expressive build system and develop and focus on the incremental build algorithm for configurable systems. And finally, for researchers to evaluate the potentials of incremental build system to support variability and to automatize the kind of heuristic to find an optimal order to build a set of configurations. The artifacts are available and reusable, and you can check it with the link below. Thank you.
Thank you very much. Very interesting. And so, yeah, let's move on and then we can come to the discussion. So our next talk will be Clemens, and it's on causality in configurable software systems.
Hi, everyone. Can everybody hear me and see the slides?
Yes, it looks good.
Yeah, then thank you very much for your interest in our paper, Causality in Configurable Software Systems. This is joint work of Christel Bayer, Christos Weiss, and Sven Apel. And the motivation for this is here as in the session configurable systems. And in fact, almost every practical software system is configurable nowadays. Let it be on a lower level on if-def constraints, software product lines, or in a daily use in system preferences. The main challenge there is that we have exponentially many system variants or configurations depending on your configuration options. And this ranges from development, testing, formal analysis, and also to explain the results and the impacts of these configuration options. And fortunately for the development and testing and formal analysis, we have dedicated approaches at hand to solve these issues. But for the explanation, there's still a lack. And this is addressed here in this paper where we present a generic approach based on this testing and analysis results to explain the reasons for and the impacts of configurations options to effect properties. Namely, we ask the question, which features and options cause an effect property? And an effect could be, for instance, in our daily use case here for fixing some internet connection that you want to have a small probability of failure or disconnect and so on. And you want to find the options here, how to select them or deselect them to ensure the small probability of failure. And given these techniques, these dedicated techniques to analyze configurable systems, we assume the valid configurations, feature configurations as input, and the results of such an analysis, for instance, the small probability of failure as effect configurations, those configurations that show the effect collected in some set E, and all other configurations we assume to be non-effects not showing the effect. And now our feature courses are somehow partial configurations where we have dedicated selected features and dedicated non-selected features, which are here indicated as plus and minus features. And our causal definition is then inspired by Harper-Pearl actual causality definition, which is the seminal causality definition there. And it comprises two conditions, namely sufficiency and counterfactuality. Sufficiency says that, okay, all the configurations that are covered by the cause, namely they select the plus features and deselect the minus features, and all the other features are not relevant, they have to be inside the effect set. They have to show the effect. And the second one is the minimality condition or the counterfactuality condition. If we would drop some of the conditions here, the plus features or minus features, then we could reach a non-effect, which then is a witness that it cannot be a cause for the effect. And our main theorem stems from prime implicant computation used in circuit optimization, and we can show correspondence between them and use prime implicants as a black box method to compute these feature causes. But unfortunately, there can be still exponentially many feature causes, and that's why we need some kind of heuristics or explanation facilities to explain these exponentially many feature causes and these impacts. And one of the facets we discussed in the paper, and I want to present here, is how to quantify the causal impact of features onto the effect. And this is based on Chokler and Harper's notion of responsibility in plane, where we have the degree of the feature responsibility of some feature X in one effect configuration ranges from 1, which is full responsibility, to 0, which is standing for no responsibility, for instance, if the feature is not causally relevant in the context eta. And if we have a probability distribution over all the effects, then we can have here the expectation over all the contexts of the responsibility, and then take the expected responsibility as a measure how much impact does a feature have in over all the effects. And as an example here, we have a Simulink control loop for a velocity control loop controller for an aircraft. And there we have 21 components here, which we can configure to include redundancies or not. Redundancies are included to increase reliability and decrease probability of failure. Here we have then more than 2 million valid feature configurations. And then we could consider the effect set of a low probability of failure, similar as in our internet connection example. For instance, we want to have an effect when the probability of failure is lower than 2.5%. And we use family-based analysis techniques for that to establish an effect set of more than 200,000 effect configurations. And for this, we can have more than 7,000 causes. This is quite difficult to explain for developers, and to evaluate these over 7,000 causes. That's why we summarize this in here feature planes, where we have for each component and each threshold here for our effect set, we have indicated the feature plane. For instance, here the acceleration integrator, they have full responsibility for ensuring this threshold of low probability of failure, which means they are causally the most relevant. And the third place is some kind of differential component here, which is has great impact, but not as much. And then we can use this for somehow rules of thumb for causality guided configuration, saying to the developer, okay, these are the 3 components you shall really protect with redundancies to increase reliability, and the others are not as relevant. We have even further results. We applied our feature causality setting to a lot of real-world software systems, performance measures, and so on. We described other methods to explicate feature causes, like with propositional logic formulas, cause-effect covers, but also we considered feature interactions, and we have a nice connection between feature interactions and minimal feature causes. And we extended this also responsibility and blame measures also to feature interaction, and could discover an performance bug in RSHIP. And if you are interested, take a look at our paper at arXiv and try out our implementation, which is available and reusable at GitHub. Thanks.
Thank you very much, Clemens. And let's move quickly along to our final talk, and then we can get into some questions. So I think to finish, we have Edward.
Yes, hello. Can you hear and see me? See my slides?
Yep, we can see the slides. We hear you whenever you're ready.
Hello, everyone. My name is Eduard Baranov, and our work is called a Scalable Device Coverage Estimator. It's a joint work with my colleagues around the world, Surav, Axel, Kuldeep, and Vinod Chatran. And we return to the configurable systems and to their testing. So when we want to test them, first of all, it's obviously not enough to test a single configuration, a single system. But at the same time, it's not feasible to test all of them. Their number could be immense. Therefore, what we are limited to is to test a small subset of configurations. And what do we want to see there? Usually, we want to see different features, how they interact with each other. Is there any interference between them? So therefore, we want to see many different combinations of features. And one of the most known metrics to measure the coverage of feature combinations is called T-wise coverage. And in principle, it's a ratio between 2 numbers. So the number of distinct feature combinations of size T appearing in the test suite, and the number of distinct feature combinations that actually satisfies the constraints of the configurable system. So the the total number of existing feature combinations. And when we want to compute the T-wise coverage, we actually see a problem. So when we have large systems with thousands of features, for t equal 2, it already takes quite some time. For t equal 3, it's really hard. And for t equal 4, it's basically infeasible. But at the same time, we really need a precise value of T-wise coverage. Some reasonable approximation is often enough. So our question was, can we build algorithms to approximate T-wise coverage and make them scalable? And the answer is yes. In particular, we provide 2 approximate algorithms that compute these 2 numbers used in the ratio to compute T-wise coverage. So the first one is called ApproxCov, that estimates the number of feature combinations of size T in the test suite. I don't have time to go into the details of the algorithm. The basic idea is that it's based on the Monte Carlo method. And the second algorithm that computes the total number of feature combinations satisfying the constraints that we called ApproxMaxCov. Here we use a different idea. So we encode the problem into a projected model counting problem. So where we have a Boolean formula and a subset of variables, and we want to compute the number of satisfying assignments for this set of variables. And we use an approximate model counter to get the result. For both algorithms, we can guarantee that the result would be probably approximately correct. What it means that given 2 parameters epsilon and delta that you can set up, we can guarantee that the approximation would be within 1 plus minus epsilon factor from the correct value with the probability at least 1 minus delta. So we've tried our algorithms on multiple benchmarks. So we put 1 hour time limits and some parameters for epsilon and delta. And what we saw that ApproxCov was able to compute all benchmarks, all the suits we tried within a bit more than 10 minutes. And the test suite contain between 10 and 10,000 of features. On the other hand, when we try to compute the exact value, we actually already have two benchmarks that haven't finished within 1 hour for t equal 2. And for t equals 6, there are only a few of them that has been able to finish. For the approximate-Markov algorithm, the difference is even bigger. So having 234 feature models, the approximate-Markov was able to compute almost all of them within 1 hour. So there was only two benchmarks for t equals 6 that haven't finished. On the other hand, with exact methods, already half of the benchmark failed for t equal 2. So if we have more than 1,000 features, it's not possible to do it within 1 hour. And for t equals 6, only 5 benchmarks has finished that had only 25, 30 features there. So takeaway, so we proposed two algorithms that allows us to estimate device coverage that are scalable, that we tried on benchmarks with a large number of features and the t up to 6. And for these algorithms, we can guarantee the approximation that it would be close, probably close to the correct value. And indeed, the implementation is publicly available. It's available and reproducible as an artifact. Thank you.
Great. Thank you very much. So now we have time for at least a few questions and hopefully some discussion. I noticed there's some questions already coming in the chat. So maybe we can take those ones first. And then if people have more, please either write in the chat or just shout out when time comes. So maybe just starting at the bottom here. So we have a question for Aaron. A small question to clarify. You are using heuristics to find good compile orders. Did you also check whether they are globally optimal with respect to compile time?
So by globally optimal compile time is the whole chain, right? Not just the pairs.
Yes, the complete factorials like n factorial, this exponential globe of all combinations.
Because we tested all of the possible cases in our paper.
Yeah.
And then we took the pairs, and of course we didn't build the chain, but we just give an indication that the chain could be an optimal order.
No, yeah, because you summarize it and said, okay, you find the optimal order. In fact, you are indeed only finding good orders, aren't you? Or are you
I didn't get this.
Are you ensuring optimality of the orders, of the compile time orders, or do you have heuristics? Because you said
yeah. So we don't have. So the future work is to find an heuristic to find the commonalities between the configurations, such that we can determine this optimal order. But in this paper, we built we did all possible incremental build of the configuration set, and then we compared with all the combination, all the chains, and we took the one that is faster than the others.
Okay, thanks. Which means you're not having a heuristics, but really
no, not yet. Not yet. Okay. We're working on it. Thanks for the question.
And I think maybe there was one more, which is
for me, yeah, I can answer.
Yeah, for you, which is about the correlation between the total build time and the chance of correctness in the binary.
Okay, so I think I have three. I can answer on 3 points to that. So the first one is we can say that when there is an error, it's faster. You know? It compiles, and you have a compile time error, and it's faster, but the binary is incorrect. The binary may be not produced, or it's the previous binary, so it's not the binary for the current configuration. You have other cases where it's faster, so maybe the incremental build algorithm is just faster. And in those cases, for instance, in the paper, we had cases where it was faster and still correct. And we have cases where it's faster and incorrect. You have cases where it is slower. So the slow case is when you have two configurations that don't have that much of artifact in common. So for the next build, the incremental build actually do a clean build. It does a clean build, and in this case, it produces a clean binary. But I think we still need to dig a little bit more on that. So here it's an exploratory study, but I think we should dig on do the metadata of the previous build have an impact on the incremental build? Because we can ensure that a clean build is reproducible, but for incremental build, we have to check if an incremental build is reproducible, which is not the same as for a clean build. So that would be my answer.
Wonderful, thanks.
Thank you.
Okay, and maybe we can do Ari's other question, which is for Clemens, which is about, in your approach, can the configurations be changed at runtime with dedicated unselected features served as A/B alternatives for different customers?
Yeah, thank you very much for this very nice question. In fact, we are currently working on that, doing some kind of including temporal aspects into the causality notion. Actually, there is not so much work done before already with when you have an operational system like a transition system or a reconfiguration automaton, how to find out causal relations in these settings. But we are working on that in the general level in our group, and me in particular working on this, transferring it to configurable systems.
Wonderful, thanks. Yeah.
And I had actually a query for Clemens while we were discussing that work, which is it gave me the reminded me about work like fault injection or for distributed systems, where you were trying to determine if I take this component out, does everything break? Is there a link there that you could make?
Yeah, for sure. That's a very interesting question, especially whether the importance. Actually, I have a master's thesis we are working on right now. How important are components or variants in the relation to causal effects? Which means if you have a fault injection, you drop out the component, does this has an effect? And you can, with the classical techniques for fault injection, they want also to estimate the impact. And we compare this right now to the causal effect. And this, it's a very nice question. But I think there's plenty to work to do. I think happy if anyone helps, because this is, I think, a huge space for continuing work.
Yeah, it sounds like, especially as systems become more complex and have more components and, as you say, more configurations, knowing the effect or the importance of each one will be important.
Yeah.
Great. Let's check here. Let's go to a question about Edward. We've got a question from Angelo, which is, do you consider how the model is constrained, like ration valid configurations or all configurations, and the frequency that you hit invalid products?
Yes, so we didn't measure how many, what is the ratio between valid and all configurations in the benchmarks we used. So we just take some benchmarks that were publicly available, and from what we saw, there are a large set of constraints in all of them. So it's not like 100% of them are valid, but I cannot really say what is the percentage there, what is the ratio. And however, for the frequency of invalid products, so what's there is interesting. So we took the feature models, and then to compute the second number that we used with approx.max.conf. However, to compute the first number, so the number of feature combinations in the test suites, we actually took 3 tools and generated test suites from them. So some products with them, and it depends on it depends on the tool. So some tools that are guaranteed to generate the only valid product. And there are other tools, and one of the tools actually was making more test suites, and then some of them are invalid and they have to be filtered out. And from what I remember, in general, there were maybe about, on average, I would say there were about 50% maybe. So we had 1,000 products in a test suite, and for that tool, we in general generated 2,000. Though, for example, on one of the feature model, it was infeasible to generate 1,000 products. So there was that many invalid configurations, and actually they were interestingly placed. So it was hard to actually. It's not if you consider the whole space of configurations, there were really small areas with valid ones. And therefore, for that benchmark, it was not possible to generate 1,000 valid products because of that. And so in that benchmark, we actually wasn't able to, we haven't used that test suite in the evaluation. So I hope this answers your question.
Like to follow up at all, Angelo? Or? He's happy.
There is a thanks in the chat.
Good. Looks like you did well. I had a question actually coming back to Kevin's talk from the beginning, which was about, you talked at the end about like having, I wrote it down, what was it? A common language around experimentation. And I wondered if you could tell us a little bit about that.
Yeah, good question. What we found during the interviews is that people have a broad range of talking about experimentation. So the most minimal thing is that people just try something and see if it works. So there's no control group or anything with that. I think the next level is doing some kind of pilot group so that you have a constraint on the number of customers that see a specific experience. Again, there's no strict control group in place. And on the other end of the spectrum, there is a clear control group in place so that you can actually compare and control for all the other possible factors in place to see what the actual result is. So what we found is that some people say that they are experimenting, but if you look at the strict definition, they're actually not really experimenting. So I think it's important thing to take into account that we create some kind of common language. What is it actually? What is the standard that we're trying to achieve? And of course, I think it's good that people just start with the basics, just try new things, right? I think it all starts with something new. But in the end, if you want to increase the trustworthiness, we need to take a step forward.
And how would you say, like in the company, how were they trying to advance that? Is it about education for the engineers in order to do that better, or is it about providing a platform for them to experiment with? What was the most common?
Yeah, so it starts with education. So there at ING there was a major training program teaching people how to take a structured approach to innovate new products and services. So I think the clear definition was shared there. Many people who had taken those lessons, they were sharing the common definition here. So I think that was an important step. But then again, if you don't support it with the appropriate tooling, then it's hard for people to actually do it in practice. So I think it starts with education, but you quickly need to follow up with the tools and processes that needs to be in place.
Great. Any other questions from the floor at this point?
I think I can answer to the question of Edward.
Oh yeah, sure, go ahead.
So for this paper, we just explored the incrementality for configurations because the incremental build system are often evaluated on the small changes during the development of a software, or small changes in the commits between two versions. And in this paper, it's really a high-level perspective on does it work, and is it possible to accelerate the compilation of a set of configurations, and so on. So, but on to detect, because it would be interesting for our future heuristic to detect if it can build or not, there are some well-known failures, some well-known limits of make fails of make, let's say, for instance, overlapping build rules, because when you configure different configurations, you don't have the same make fail. It changes when you configure, so you have to maybe compare and check if there are overlapping building rules. And if you need to force some library, because sometimes you have the same name for a rule of a library, but the configuration needs a new function, but the configuration before didn't compile this, and the make-fail sees that the rule has been done and it doesn't do it anymore, but you still need to build it for the current configuration. So these are the kind of schema we can find in these errors. And we discussed a little bit about them in the paper, but as a future work, it would be great to characterize first the kind of changes between configurations and how a build system could handle it, and how to test even broader build systems. Here it's for Make, because it's the most common software with Make and that are highly configurable and used often in the ML community. But we want to check even more, for instance, in Bazel or Java project, for instance, how it behaves for configurations. And we want to explore more test questions.
Okay, thanks a lot.
Thank you.
Okay, maybe we have time for one more question. I had a question for Anastasia. She's still here, which was just to understand. I think the tool looks very interesting, and if I understood correctly, you can use it to find all of the reflective code within the code base. Is it that you are trying to transform that code in order to make it more efficient to compile, or more efficient at runtime, or what's the real thing that people would use the tool to do?
Okay, we have two scenarios for using this tool, and the first one is the simple scenario when you have some projects with reflection calls, and you want to looking for functions or classes or objects, and you just use our DSL to put your query with conditions to find for classes, functions, and during compilation, this the whole query will be replaced by to the list of the found entities, but it's not in the source code. I mean, Kotlin compilation process is difficult, and it has intermediate representation. It's a common representation for several platforms, for JVM, for Kotlin native, and for JavaScript. And we replace this query on this level. And next, the Kotlin compilates it to bytecode, for example, or to JavaScript for JS. And in bytecode, the reflect query will be replaced to the list of entities, but the source code will be original and without any changes. Yeah. And in the future, we would like to support Java and analyze Java sources because a lot of Kotlin projects, it's a part of a big Java projects, and we will analyze not only Kotlin files, but Java files, and we can replace it on the year level and on the bytecode level, and we will not use some special annotations, since user can use any annotation, for example, and user can use any condition for filtering. We didn't find any tools which supports this feature, because it's difficult in the common cases to know what user wants. And for this approach, we use Kotlin script. It's Kotlin interpreter, and we get the user condition and run interpreter of Kotlin at compile time of the project, yes, and get results and replace representations.
Yeah. So it's a complicated pipeline.
Yeah. But we have the second pipeline when, like Kotlins, for example, Kotlins have reflect queries, but it should be replaced not on the Kotlins compilation. It should be replaced on the project which use Kotlins as a library. Yes, and reflect works for this case too. And for this one, we during Kotlin compilation, we collect all reflect queries and their arguments, serialize them, and after that, during project compilation, which uses Kotlin, we extract all queries and found all entities which satisfy these queries, and create a special file with all answers to all queries. Yeah.
Oh, very interesting. I think I have to go and check the paper for some more details. So I think we just
Thank
got about to the end of our time. So thank you very much to all of the presenters for this session and for all of the questions and discussion. And I'm sure you'll be able to catch people in the coffee rooms and in the other sessions over the next few days. So thank you very much.
Thank you very much for the session.
Yeah, thank you. Bye.
Thanks.